Hello, this is Mr. White, and this video is on summations. Here are the 3 exercises for today. Okay, let's clear out these 2. And the mistake students often make with this first one, or textbook exercise similar to this first one, is that students jump to the conclusion that it's all about using these summation formulas. And those will be essential to us, but let's take a look at what we're being asked to do here. Look carefully at the sigma and how many terms is it that we're exactly going to be adding up. Well, if we start with j equals 5, 5, 6, 7, we end with 7, we're really only adding 3 terms, so we might as well just write this out. And really the purpose of this type of exercise is to see, do you understand what sigma notation is telling you to do? So again, you certainly could use the formulas if you felt like getting extra practice, but let's not. Let's just remind ourselves that this sigma notation is telling us to start with j equals 5. So start with, we might call it a sub 5, the 5th term if you like, plus the 6th term, plus the 7th term. And as far as what each of those terms equals, to find the 5th term, plug in 5 and 5, and we get 5 times 5 plus 1. Okay, that's going to give us 30. And then the next term, 6 times 6 plus 1, that's going to give us 42. And finally, 7 times 7 plus 1, that's going to give us 56. And that gives us 128. And that's 2 to the 7th power. How cool is that? So again, sure, we could have used these summation formulas if we really wanted to, but it would have taken a lot longer. And I also will point out, these summation formulas do have their limitations. If this original summation that we were given was something like 1 over j times j plus 1, notice that the summation formulas cover adding up a bunch of constants, or I squared, I cubed. You can think of it as j squared, j cubed. But there's no summation for 1 over j. So when you start getting into things like reciprocals up here, the summation formulas we're going to find have their limitations. So as far as using the graphing utility to verify our result, let's bring the calculator up here. And this is something that only works on the TI-84s, not the T-83s. There are some programs on the internet that can kind of make it work for the TI-83s, and you can certainly ask me about that if you'd like some help with that. But on a TI-84, go to Math menu, and if you just remember that it's option 0, you can certainly press 0. If you really want to see it, I'll press the up arrow button, and we see that there is, at option 0, is summation. So you could hit enter at this point, or just type in 0. And it doesn't really matter. In our original problem, we were dealing with j, but as long as it's the same index of summation in all of those locations, it doesn't really matter. So I'm just going to pick the easiest thing, which is x. We typically don't really use x when we're writing summations on paper, but for the sake of the calculator, it'll suit us just fine. And then just type in that expression, x. And if you really wanted to type in j, of course you could. You could use the alpha characters on the calculator and type in j. But I hit enter and verify that it's 128. But as we will soon find out if we haven't already, the calculator is great for checking, but there's it's going to have its limitations too. So we better understand how to do it by hand like we did over here. All right, let's get to exercise number 2. So for this exercise, the series is written out in long form here, and we're to write it in sigma notation, aka summation notation. And we want to start by really just focusing on what's changing and what's not changing from term to term. We can see that this 5 over n is not changing. We can see that on the bottom, we see n plus, that is not changing. What is changing is that root 3, root 3, root 4, root 4. Now, if you look at what's happening on that last term, we need to resolve something here. We said that the 5 over n was not changing, right? So highlight that. However, we also said that over here, on the left, that the n plus there would be the same, right? And at first glance, it doesn't appear that we have that here, but we can make it appear. Let's rewrite that bottom one as n plus n minus 1. And isn't that the same thing as 2n minus 1? And when I look at it that way, we get a pleasant surprise here because, yes, the n plus is the same. And furthermore, we see a continuation of this pattern we saw in the initial terms. We had root 3 over 3. We had a root 4 over 4. And here the pattern continues. Root n minus 1 over n minus 1. So let's get into the sigma notation. And let's start with the things that are staying the same. We know that the explicit rule for each term in the series is going to have a 5 over n. We know there's going to be a fraction in front of it, and that there's going to be an n plus on the bottom. And now we just need an index of summation, or like such as the letter I or j as in the previous exercise. That's what represents what's changing. So I see that where I have a root 3 over 3, root 4 over 4, etc., I'm going to put root I over I. And then I'll put down here, underneath the sigma, the starting value for I. And again, we look at the first term there, and we see that we started with a 3. And then we look at the last term, and we say, what was there in that I position? An n minus 1. And that, ladies and gentlemen, is our final answer. So just to kind of recap here, if I cover up the I, and I imagine plugging in the initial value of I, 3, I put it here and here, I get the same thing as my first term. I get my first term there. Whereas if I plug in the last value of I, n minus 1, n minus 1, I'll see that down here, again, that's really 2n minus 1, and that gives me my last term up there. All right. And here it is color-coded for your viewing pleasure. All right, so let's go on to the last one now. So here's the big one, for this video at least. We're going to take this crazy, cryptic, abstract-looking summation and rewrite it without using the summation notation. In other words, we will be using the summation formulas. And then we're going to plug in these values for n equals 10, 100, 1,000, and also find the limit as n goes on to infinity. This, I assure you, is not a totally random pursuit. And while I hesitate to get too far ahead of ourselves, just to help motivate you to get through this and start seeing the connections right off the bat, I'll go ahead and tell you that what this whole crazy summation represents is the area, a calculation of area under the curve. And the function that it's dealing with is x squared plus 6. And I'll invite you to look at the summation and kind of see the x squared plus 6 embedded in there. And we're finding the area from x equals 1 all the way to x equals 4. And I'll invite you to pause the video as needed, start looking at that and trying to see the connection here. When you think of this concept of embedding rectangles underneath a curve, and how when we want to find the area of the curve, we're really going to start by finding the area of all those rectangles. Think of how this represents the base of the rectangles, and how this is going to represent the height of the rectangles. This says to add them all up, and ultimately when we plug in 10, we're really saying what's the area of 10 rectangles crammed underneath that curve. Then 100, then 1,000, and think of how the limit, as you approach infinitely many rectangles, how that's going to give you the exact area underneath this curve. It's a pretty cool process. Okay, so again, start looking ahead to that, start thinking about making those connections, but we need to make sure we can handle all the algebraic processes here, so let's get to that. So as far as how we're going to tackle this goes, let's look ahead a little bit And remind ourselves that what we're ultimately going to do is, or not ultimately, but at some point in the process, we're going to take these sigma formulas. We need to strip the sigma down to just sigma I, and or sigma I squared, and or sigma I cubed, and or sigma and a constant. And we can certainly have multiple sigmas if need be, but we need to start by getting it down to this point. And then once we've got that, then we can substitute in the respective formulas here. Okay, so with that in mind, let's move those formulas off to the side and start trying to strip this down here. I'm going to start with this 1 plus 3i over n quantity squared. And remember, that's really just 1 plus 3i over n times another 1 plus 3i over n. So this is nothing more, nothing less than our typical foiling, where we'd get 1 plus 3i over n plus another 3i over n, 6i over n, plus the last term in the FOIL will give us 9i squared over n squared. And that has a plus 6. That's just this plus 6 up here. And that's inside brackets 3 over n. Okay, and let's continue to simplify. Notice we have like terms here. We have a 1 plus a 6. So that's going to give us 7. And let's go ahead and at the same time distribute this 3 over n on the outside. So 7 times 3 over n will give us 21 over n. 6i over n times 3 over n will give us 18i over n squared. And 9i squared over n squared times the 3 over n will give us plus 27i squared over n cubed. And remember what I said earlier, that we want to just strip this down to where we have sigma I squared. So let's do that in this next step. Let's remember that for our purposes, although in some sense n may be thought of as a variable, for right now, treat n as a constant. Think of it as a constant, as if it were the number 5, for example, or any other constant. So, as such, remember you can bring constants to the outside of the sigma. So, for example, I can bring a 21 over n to the outside of the sigma and just have a 1 on the inside. Because 21 over n times 1 will give me that 21 over n. And I can also split this sigma of a sum into the sum of multiple sigmas. So I can do plus another sigma. And here I'll get that I that I wanted to have. I'll go ahead and put it by itself here. And on the outside, I'll bring the constants. Treating n as a constant as well as the 18, we can bring 18 over n squared to the outside of the sigma. And finally, for that last term, I can get the sigma, I can get the I squared all by itself, and bring this constant to the outside. So 27 over n cubed. Okay, so here is where we bring in the summation formulas. So I'll line them up underneath and move these over a little bit. Okay, and let's do some substitution. So in this case, the constant in this first formula, the c is really just a 1. That's what we've got up here. So this is telling me that if I add up the number 1, if I add it up n times from 1 all the way to n, I'm going to get just n. That makes sense. So let's replace this summation with just an n. And the 21 over n in front. How about this summation? We'll replace that one with the appropriate formula, n times n plus 1 over 2, with the 18 over n squared in front. And finally, the summation for I squared. I just realized I was inconsistent there. We'll replace that with n plus 1, 2n plus 1, and we've presumably gone over in class why these formulas are what they are. And of course the 27 over n cubed in front. Okay, and I did just notice the mistake I made back here in the middle one. That's not an n on the bottom, that's a 2. But I'm not going to redo the whole video just for that. So from here, it's just a little bit of messy algebra. Multiple ways you could go about it, but I would certainly start by just canceling out or dividing out whatever I could. Those n's go away. This n up top can do away with one of the n's down below. This n up top can do away with one of those n's. That becomes n squared. And at this point, I would just FOIL out, for example, FOIL that out. Or actually, you know what, before doing that, let's say that 18 and that 2, those reduce to just a 9 up top. Likewise, this 27 and this 6 reduces to 9 over 2. And this is actually getting messy enough where I think it's time to rewrite. So we've got 21 plus, let's see, 9. I'll go ahead and distribute. So 9 times n plus 1 will give us 9n plus 9. And that is over n. Plus, let's do it this way, 9 over the 2n squared. And let's go ahead and distribute that out. Let's FOIL that out and get 2n squared plus, let's see, it's going to be n and 2n. It's going to be 3n plus 1. And again, there are multiple ways one could go about this. You may be looking at this and thinking, oh, we're probably going to do a common denominators thing, which would be fine. That's not a bad thing. But given where we're going with this, I'm actually going to do the opposite. Rather than combine these all into a single fraction with common denominators, I'm going to break it completely apart. And I think you'll see why as we go through this. So let's just leave that there as 21. And let's break it apart. 9n over 9 will give us just 9, right? Plus 9 over n. Now, 9 times 2n squared over 2n squared will give us plus another 9. Distributing 9 times 3n over 2n squared. That will reduce to, let's see, 27 over 2n. Notice that I divided out an n in that term. And finally, 9 times 1 over 2n squared gives us 9 over 2n squared. Okay, let's combine our like terms. 21 plus 9 plus another 9. That would give us 39. Plus, I suppose I should be circling the plus signs as well. Plus 9 over n plus 27 over 2n. Be careful. To do a common denominator, if we're going to combine those, I really need to do 2 times 9 over 2 times n to get my common denominator. And that will give me 18 plus 27. That'll give me 45 over 2n. And finally, plus 9 over 2n squared. As far as our original, as what we're supposed to do, if we've lost sight of that, we were to rewrite the expression without using summation notation, and we've done that and fully simplified it. And next we'll plug in those n values of 10, 100, 1,000, and then take the limit. But since we've already completed part 1 of that task, let's put a box around that. And as far as, let's see, evaluating at these different values of n, let's use our calculator for that one. And I'm going to do it in a way that I think is a very efficient and cool way to do it. Let's go to y equals. And anytime you find yourself doing a repetitive calculation over and over again, you may consider something like what I'm about to do here. Let's type in this expression. Of course, we'll have to use x instead of n. But we'll do 39 plus, we'll do a fraction, 45 over 2n. But we'll type 2x instead, plus, and then another fraction, 9 over 2n squared. Of course, if you're on a TI-83 and you're typing this out, 9 slash, make sure you do parentheses, 2x squared. You're probably used to that caution by now. And rather than go to the graph, or even rather than go to table, I'm going to quit. And I'm going to go to alpha F4 and choose my Y1. Or I'll remind you, on TI-83 users, or TI-84 users, you can go to vars, arrow over to y vars, hit enter for function, and then get Y1 that way. And I'll do parentheses. I'm taking Y1 of 10. And I see my result. I can go to second, enter, and then just insert another 0 there. And I see the next result. Second, enter. Let's go to one more 0. And then close parentheses here. And so this is what exactly I'll put on my paper. Bit of a lazy shorthand here. I'll just put sigma equals. It's understood that the only sigma we're dealing with is the one from the beginning of the problem. And I'll just put sigma is going to be 41.295. And I'll remind you, in the broader context of things, what this is really saying is that when you cram 10 rectangles underneath the curve on the interval I mentioned earlier, the area of those rectangles will be 10 rectangles will be 41.295. Rounded off to 3 decimal places. If I were to cram 100 rectangles underneath that same area, I would get the area of those rectangles being 39.225, using the AP standard of just 3 decimal places. If I were to cram 1,000 rectangles underneath, those 1,000 rectangles would collectively have an area of 39.026. Excuse me, not 026, 023. And finally, as I cram more and more rectangles, not only does this appear to be leveling out to 39, but even more compelling, look up here, and we can tell as n goes to infinity, these two terms will disappear, will zero out, and we'll get just 39. All right, good stuff.